Welcome to the first in a series of introductory videos on molecules and covalent bonding. Previous videos, linked in the description below, investigated ionic compounds, compounds made by the exchange of electrons between positive cations and negative anions. Molecules made by covalent bonding are made by sharing electrons. In this case, purpose is still the same. All of the atoms are now sharing electrons to obtain noble gas configuration. Which type of bonding one applies depends upon the position on the periodic table and periodic trends. For review, ionic bonding involves cations giving up electrons to negative anions and the positives and negatives attracting each other. Covalent bonding, on the other hand, involves the sharing of electrons to form molecules. Again, these are the extremes. In reality, there's a gradient between the two of them. In terms of the bonding trends, we've already seen that the metals exclusively form cations and form ionic bonds, where everything in group 1 being +1, everything in group 2 forming a +2 charge, and the charge of the remaining metals depending upon balancing out so the entire compound adds up to 0. Nonmetals and semimetals have several options. When bonding with metals, they form ionic bonds, where they form the anions, with group 6 always forming a charge of -2, and group 7 always charging -1. This again is to make sure that everything can reach the noble gas configuration. Once one is bonding within the nonmetals and the semimetals, you will now have covalent bonding to form molecules. Either way, through ionic or covalent bonding, the entire point is to achieve a noble gas configuration. When looking at the covalent bond, several things happen. First of all, there is sharing, and sharing all outer shell valence electrons between all of the atoms. Each bond consists of 2 shared electrons, where one electron is provided by atom A and the other electron is provided by atom B. Also, at the end, when all the electrons are shared and redistributed, every atom within the molecule will achieve noble gas electron configuration. This is called the octet rule. Essentially, the octet rule comes from the fact that all elements will receive the same number of electrons as the next nearest noble gas, which is in group 8, hence the octet. Practically speaking, most molecules we're familiar with are based on carbon, small elements, which means this usually involves actually each element having 8 electrons. Something called a Lewis structure is a very powerful tool in understanding how molecules are assembled and how they will behave. Essentially, a Lewis structure is a picture of the molecule. It's drawn in such a way that every atom present in that molecule fulfills the octet. And it's useful because once one realizes or determines what a molecule looks like, one can determine the shape. And the shape of the molecule, as you'll see in future videos, goes a long way in determining how that molecule will react. So to start with, Lewis structures are based on a system. So the easiest way to investigate them is to go through the system. Take a simple molecule, CH3Cl. The point of covalent bonding is to share valence electrons so that everybody reaches noble gas configuration. Everybody has a full octet. So the first step is to count the valence electrons available. If one looks at the periodic table, carbon has an electron configuration of helium 2s2, 2p2. Hydrogen is 1s1. Chlorine is neon 3s2, 3p5. The valence electrons are the electrons outside of the noble gas. So 2 plus 2, carbon will have 4 valence electrons. Each hydrogen contributes 1, as there are 3 hydrogens, that makes 3 electrons. 2 plus 5, chlorine contributes 7, so there will be a total of 14 electrons shared. Understanding the periodic table gives you a very simple shortcut to determining the number of valence electrons. If one looks on the periodic table, one sees that carbon is in group number 4 and gets 4 electrons. Hydrogen is in group 1, and each hydrogen gives 1 electron. Chlorine is in group 7 and gives 7 electrons. The number of valence electrons can easily be determined by simply looking at the group number of the element. Once those electrons are determined, one then has to figure out how they will be distributed. The second step is to draw a skeleton. The skeleton is made by connecting the atoms by single bonds. As everyone is trying to get to group 8, the number of bonds that any given element can make is going to be 8 minus its group number. So in this case, carbon in group 4, 8 minus 4 means carbon forms 4 bonds. Chlorine in group 7, 8 minus 7 means chlorine forms 1 bond. So therefore, one of those bonds will go from carbon to chlorine. Finally, as we'll go in with more detail later, hydrogen's octet is actually to try to get to helium, because 1s2 gives you 1 bond for hydrogen, gets you to the noble gas helium. So, as a skeleton, I have carbon with its 4 bonds, 1 bond each to hydrogen and chlorine. I account for those electrons then. 4 bonds have been made. There's 2 electrons for bond. That means I've used 8 and have 6 left. For the remainder, hydrogen only wants 1 bond. So the hydrogens are satisfied. Carbon has 4 bonds. 4 times 2 is 8 electrons. The carbon is also satisfied. As drawn, if I look at chlorine, chlorine only has 1 bond attached to it, which means it needs 6 more electrons. However, I have 6 electrons remaining, which means they will get distributed on the chlorine. And that will be the Lewis structure of CH3Cl. Lewis structures are best done essentially by practice. It's a systematic method, and when one gets used to the system, one can do Lewis structures. So a couple of other molecules. Simple things. I start with water. Valence electrons. Oxygen's in group 6, therefore it has 6 electrons. Hydrogen's in group 1, therefore 2 hydrogens give 2 electrons. I have 8 electrons. To draw the skeleton, oxygen is in group 6, which means 8 minus 6, oxygen draws 2 bonds. I have two hydrogens to put one on the end of each bond, so that's my fundamental skeleton. In doing this, I have formed two bonds, which means I've used up 2 electrons per bond, or 4 electrons, so I have 4 remaining. To distribute those 4 electrons, I note hydrogen only forms one bond, so hydrogen's happy. However, looking at the picture once again, oxygen has 2 bonds and only 4 electrons. The magic number is 8, so it needs 4 more. I have 4 left, so those electrons go to oxygen. And this is what a water molecule looks like. Another common example, ammonia. In this case, nitrogen is in group 5, so it gives 5 electrons. 3 hydrogens will give another 3, giving me a total of 8. Nitrogen, being in group 5, is going to form 8 minus 5, is going to form 3 bonds. There's a hydrogen on the end of each of those bonds. 3 bonds has used up 2 electrons each, leaving me with 3 times 2, 6 electrons used. I have 2 electrons remaining. Again, the hydrogens are happy. Each hydrogen has 1 bond. They are satisfied, but if I look at the picture and I look at the nitrogen, nitrogen only has 6 electrons and it needs 2 more to get to the magic number of 8. However, I have 2 electrons left, so they go to hydrogen and that to nitrogen rather, and that is what ammonia looks like. A more complicated molecule, but common still, carbon dioxide. It's very simple to have no preconceived notions, just simply go through the steps. I count the valence electrons. Carbon is in group 4. Each oxygen in group 6 gives 6 electrons, so that's 12. I have a total of 16. I draw my skeleton. Carbon can form up to 4 bonds. Oxygen can only form 2 bonds. Therefore, since carbon forms the most bonds, carbon gets to go in the middle. So I draw a skeleton where carbon is attached to 1 oxygen on each side. I count my electrons again. Oxygen has 1 bond and needs 6 more. Carbon with 2 bonds needs 4 more electrons. The oxygen on the right, 1 bond needs 6 more electrons. So as drawn, this structure is 16 electrons short. However, I have 16, but I only have 12 left. This creates a problem because I'm obviously missing 4 electrons. The entire point of covalent bonding is to share what you don't have. So if each atom is missing electrons, you wind up sharing. If I'm missing 4 electrons, that's the equivalent to forming 2 more bonds. I add 2 more bonds. That uses up 4 more electrons, leaving me with 8 now. I go back to my electron counting. As drawn now, carbon is fine. Each oxygen with 2 bonds needs 4 more. So I need 8 more electrons. I had 2 more electrons. So each carbon gets 4 electrons. Each oxygen rather gets 4 more electrons. And you have the structure of CO2. A final example with a nuance. A carbonate ion. As you know, a carbonate is a CO3 molecule, but with a charge of -2. So first of all, when counting the valence electrons. Carbon, being in group 4, will donate 4 electrons. Each oxygen in group 6 gives 6 for a total of 18. However, I have a -2 charge, which means two more electrons were added. So accounting for those, I have a total of 24 electrons to deal with. For the skeleton, carbon can make up to 4 bonds. But in this case, it only needs, for starters, to make 3, 1 to each oxygen. That takes care of 6 electrons, leaving me with 18. However, I need 20, as each oxygen needs 6 and carbon still needs 2. I am now 2 electrons short, which means I will add another bond, leaving me with 16 electrons. Relooking at my needs, the oxygens on the left and right each need 6. The oxygen on the top needs 4 electrons to reach 8. Carbon needs none. So 16 electrons are needed. I had 16. So 2 of the oxygens get 6. The oxygen with the double bond gets 4 electrons. Everybody has an octet. With ions, something else has to happen. Essentially, 2 more electrons were added to this structure. One has to make sure the viewer knows that those were added on purpose. So first of all, if you have a molecular anion, they are always placed within a square bracket, and the charge is shown on the outside so that everybody knows there are supposed to be 2 extra electrons in there. Looking closely at the carbonate, you will notice one other thing. There's a double bond to the oxygen on top. However, starting with the original skeleton, there is no difference between any one oxygen or any other oxygen. So I could very easily have written this as having the double bond on top. I could have the double bond off to the right, or I could have the double bond off to the left. Question is, which one of these Lewis structures is correct? The answer is either none of them are totally correct or all of them are partially correct. What actually happens is you have what is called resonance. Essentially, whenever you have 2 or more equivalent Lewis structures, as shown here, where the only difference between those Lewis structures is where a identical double bond, in this case a C double bond O, is placed on top, to the left, to the right. In that case, none of the Lewis structures are 100% correct. The correct answer is something in the middle. Essentially, all 3 of these exist in equilibrium, with the double bond always moving around. So that concludes an introduction on how to draw Lewis structures. In videos that follow, linked below, you'll see why it isn't so important to draw them and what they can tell you. Thank you very much, and I hope you found this useful.